Tim Beiko, and today I'm going to talk about how Ethereum works in a post-merge world. So let me share my slides here. Okay, so as all of you may know, Ethereum just went through a pretty big transition to move from proof of work to proof of stake. So today I wanted to take some time to kind of share the context behind that transition, walk you through exactly what happened, and kind of give a picture of what Ethereum looks like today and how the network works. And so to take a little step back and kind of start from the beginning here, Ethereum always had this desire to move to proof of stake. It was part of the initial roadmap even before the actual chain launched. And as soon as basically Ethereum was live, work shifted to try and design a proof of stake algorithm that Ethereum could switch to. And around 2018, we had something which we almost went to production with, but ended up ditching for a few reasons. And at a high level, the main reason to move away from this was just that it was very closely coupled with the existing proof of work chain and kind of brought in a bunch of technical constraints from that chain that made the system quite worse. So first, the proof of stake algorithm was designed as a special contract, like a kind of enshrined smart contract on the network, which had different operation constraints than normal smart contracts. So it added all this extra logic in sort of a semi-detached way from the network. And the initial design also had like quite a high minimum stake required to be a validator. It was 1,500 ETH. And also, at the same time as research on this was happening, people were already thinking about how we go and scale Ethereum. And we're coming up with similar designs and hitting similar constraints for things like sharding. So around 2018, there was this realization that, well, maybe this design is not great. And then the kind of thought was, what if we just designed a proof of stake and sharding Ethereum from scratch? What would that look like if we had none of the constraints of the current proof of work chain? And so this is where the Ethereum 2.0 roadmap came about. So the idea was that you would redo everything from scratch and move all of Ethereum to this new system, which would be re-architected from the ground up and kind of perform much better than the current proof of work chain. And so when people talk about Ethereum 2.0 and the sort of phase 0, phase 1, phase 2, this was the idea. Phase 0, the idea was you would launch the proof of stake chain separately from the system and first get that up and running so that you can make sure everything works there. Then instead of directly scaling computation on the network, we would launch shards, which would execute in parallel and anchor back to the beacon chain, but they would only store data rather than execute transactions. And then finally, once we were confident that the system was stable, we would turn on computation in those shards and get all the applications to migrate to the new Ethereum. And this is kind of the roadmap that was talked a lot about in 2018, 2019, and 2020. And as you can see, we actually did do part of it. So we did launch the beacon chain separately. But there were some problems with this. It still wasn't quite perfect. The biggest open question was, if we do this phase 0, we launch the beacon chain, we do phase 1, we add these data shards. It was never quite clear how we would turn on computation in those shards and what that would look like. This also implied that we would need users to migrate from the current chain to another one, and that all the applications would have to be redeployed. People would have to move their funds over, so that would be quite complex. And then the other thing it would require is it would require new software to execute all the transactions in those computation shards. And we know just from history how hard it is to write these Ethereum clients. So we have some on proof of work, we have some for the beacon chain, and it's quite a lot of work to write and maintain these. So while these problems started showing up on the roadmap, there was another thing that happened in the space, which was kind of the appearance of rollups. And the idea there with rollups is that you can scale computation on Ethereum using layer 2s rather than the protocol itself. And so with this kind of emerging, you can see there were a couple refinements to the original Ethereum 2.0 roadmap that led us to what was the specification we ended up using for the merge. So early on, when there was this realization that it would take time to launch the beacon chain, deploy data shards, turn on computations in those shards, Vitalik put a proposal to say, what if we simply made the proof of work chain the first shard of Ethereum 2.0? So this would get us kind of Ethereum moved to proof of stake. It would allow us to test the system, and we wouldn't have to wait for all of these computation shards to be migrated. And it might also mean that there's actually no migration for users because the proof of work chain just becomes sort of shard zero of the new system. And then there's a second kind of refinement on this idea almost a year later, which was saying, what if we actually ditched this part around executable shards in the roadmap and simply focused on rollups for scaling? And the interesting thing there is that rollups generate a lot of data. Either they post transaction data back on chain or proofs of it and state diffs with ZK rollups. So the first two bits of the roadmap, having the beacon chain and having the data shards, is still quite useful for rollups because it gives them somewhere that they can post data back to. But the most complicated bit around turning on this sharded execution, that's basically how rollups work. So this second kind of rollup-centric roadmap insight was saying, well, let's just ditch the most complicated part of our protocol changes, simply launch the beacon chain, have the data shards, and have rollups kind of store their data on those data shards, and we'll have scaling for Ethereum. And then the third refinement that came to this idea was saying, well, what if we keep doing all this, but instead of having the proof of work chain become a shard of the Ethereum 2.0 design, what if we simply change what the current proof of work chain listens to come to consensus? So to change from proof of work to proof of stake. And the interesting thing there is all of the software that ran the proof of work chain already had this concept that it could change consensus algorithms. So basically on Ethereum mainnet, it would run proof of work, but on testnets, for example, it would run proof of authority, and same on private network. So if we could simply kind of reuse all that software and get it to swap its consensus algorithm to something else, and then we wouldn't have to write any new kind of software to execute the proof of work computation. We could just keep things like Geth, Aragon, Nethermind, Besu, have them swap over their consensus algorithm and move to proof of stake that way. And this is more or less the final design we've gone with. And it's worth taking a second to kind of show the contrast between what this initial Ethereum 2.0 roadmap was like and what the sort of rollup-centric approach we've taken looks like. And without even going into all of the details, just like, glancing at those diagrams, you can see that it pretty much ends up being the same thing, right? Like we get to a very similar end state. On the left side, we see there that the original plan was actually to keep proof of work around for a while, and then have that tethered to the proof of stake chain, which is something we ditched. We moved to a world where we completely just use proof of stake, and that's what you can see kind of on the right side. And then you can see that instead of, you can see that on the left side, we have all of these shards that provide data, and then the VMs that link back to them and that provide execution results. And if you look at the right side of the diagram, you basically see that a very similar thing where you have all of these blobs, which are basically the shard chains that provide data. And you have all of these L2s, which are now running the EVM. So instead of having kind of one version or versions of the EVM that are dictated by the protocol, you can have all these different implementations that are done by many teams. And they're not only EVMs. There's obviously Optimism, Arbitrum run EVM rollups, but you can see ZK Sync and Starkware that have different approaches as well. So we end up to a state where we have this kind of parallelized computation that's happening that allows us to scale Ethereum's throughput, that's using the data layer on L1, and we have proof of stake securing that. So this was kind of a much simpler design that ended up getting us to roughly the same spot. And if we zoom in a little bit into the merge, right, this transition from proof of work to proof of stake, what happened there? So first, like I was saying, the idea is to go from proof of work to proof of stake as the consensus algorithm for the network. And this means that, after this transition, what was currently known as ETH1 or the proof of work state chain becomes the execution layer for all of Ethereum. So where the transactions run and all of that. And then the beacon chain, or what was known kind of as the ETH2 part of the system, becomes the consensus layer. And as we said already, the execution layer clients already had this concept where they can switch different, they can use different consensus algorithms. So it was reusing kind of some logic that already existed. And obviously there was a ton of custom stuff that had to be developed for the merge, but generally like this concept is something that clients were already used to dealing with. And the way that we would trigger the transition is saying, once there's a specific amount of difficulty that's reached on the proof of work chain, the clients stop listening to proof of work as the way to determine the head of the network, and they instead shift to proof of stake. And then in a post-merge setting, what this looks like is that the consensus layer client, so the beacon chain, is running the proof of stake algorithm. It gets the consensus on what the head of the chain is. It's what produces and gossips the blocks, and obviously handles syncing to the right fork on the proof of stake side. And then the execution layer still executes all of the transactions in the EVM, make sure that they're correct and they follow the protocol rules. It still manages all of the state and basically the database and sync associated with that, and gossips transaction on its own peer-to-peer network as well. And if you zoom in even more in like the actual transition process, what happened was this. First, we had an upgrade on the beacon chain to tell it to listen for this terminal total difficulty value that we set, which is the highest amount of difficulty we want to see on the proof of work chain. So once we set this value and deployed the software, this was during the Bellatrix hard fork, the beacon chain and the execution layer are listening, kind of pinging every block, asking, have we exceeded this TTD value? When we see a block who first exceeds TTD, we consider this to be a candidate final proof of work block. And this is kind of the last block that's produced in that chain by proof of work. And producing the next block is then the role of the validator who's assigned in the next slot on the beacon chain. And because reorgs can happen and there can be multiple competing terminal blocks, what we want to see is once this first proof of stake block has been produced, we want to see this finalized so that we know we can't reorg past the transition. And once we had that, this is when we knew that the transition was complete. So I have a graph here by Danny Ryan who kind of shows this more visually. If you go all the way to the left here, you see we have our proof of work and beacon chains both running in parallel. On the top, you have this proof of work block, which has some proof of work, but then within it, there's all of the transactional contents of the block and the data that's required to validate those transactions, like the hash of the block, the base fee, and whatnot. And then right below that, you have a beacon chain block that has all of this data related to the proof of stake chain. You can think of it as like consensus metadata. So, the attestations, all the new deposits, all the exits, the RANDAO and whatnot, but it doesn't have any actual end user transactions being executed in it. And so if you move over one block, you could imagine this second proof of work block would be the one where we exceed TTD. So we consider that the terminal proof of work block. While that's happening, the beacon chain is still operating as it previously did. But then once that proof of work block is hit, that second proof of work block, we see that this third beacon chain block now contains the transactional payload of the previous proof of work chain. And this is basically the merge happening. It's going from this last proof of work block, which has all of the transactions in that, to basically the beacon chain still coming to consensus on proof of stake, but then including what we now call an execution payload, which is the list of all these transactions, as well as all the relevant data to execute them on the network. And then if you move over to the last block on the right, you can see that this block basically has no linking back to proof of work, right? It's a pure kind of proof of stake block, which has all of the proof of stake consensus information as well, and this execution payload again. And this is what we wanted to see finalized. It's just the first block on the proof of stake side, so that we know we can't reorg back to proof of work world. And if you zoom in even more on one of these blocks, like I was saying, the content that used to contain all of like the transaction related data of an ETH1 block now becomes an execution payload, which is part of a beacon chain block. And the goal there was to make the transition as seamless as possible, so that a transaction running in the last proof of work block or the last proof of stake block would execute the same way, that smart contracts and users won't have anything to do. That said, there are like a couple of changes that are worth noting. So the first is that the block times on proof of work were averaged to about 13 seconds, but really high variance. Whereas in proof of stake, they all happen every 12 seconds unless the validator is offline. And this currently happens less than 1% of the time. The second thing is that there were several fields in the block that we set to 0 after the transition because they no longer apply. So anything related to proof of work or uncle blocks are basically the things we zeroed out, but with one exception. So difficulty is a value that was accessible in the EVM, and it's kind of a biasable pseudo-random value that is used on chain for pseudo randomness. If we move that to 0, then it would go from providing for randomness to providing no randomness at all. So instead, what we do is we rewired this opcode to return the random reveal from the previous slot in the EVM, which is another source of randomness that can now be used by contracts. So this is really the only change in terms of like contract execution on chain, and it's kind of neat because the size of those values is different. So if you look at the size of the return value of this opcode, you can know whether your contract is executing pre or post merge. And if you look at what an Ethereum node looks like on the network, this is roughly the idea, where an Ethereum client now requires you to run both a consensus layer client and an execution layer client. Without these, if you don't have the consensus layer client, you can't tell what the state of the chain is. And if you don't have the execution layer client, you can't actually execute the blocks on chain. So you need to combine both of them. But because we wanted things to also be seamless for the users of these clients, all of the nodes still maintain their APIs as previously. So if you were using the Beacon APIs or JSON RPC or WebSockets on the execution layer, none of that changes. You still kind of get the same experience. And similarly, both kind of clients as part of the node, so the consensus layer and the execution layer, maintain their set of peers. So the gossip networks remain independent, and the only thing that changes there is that blocks go from being gossiped on the execution level to the consensus level. And then in order for both the consensus and execution layer to communicate, we've introduced an API between them, which is called the Engine API. And this is just an authenticated API where the consensus layer can send information to the execution layer, telling it, what's the latest valid ahead, what's like the state of the network, and it can also request information from it. So for example, it'll send it a block and ask it to validate the block, or similarly, if it's a validator and it has to propose a block, it will query its execution engine and ask it to return a block that it can propose on the network. And so that's pretty much it for how the network works. We work quite hard to have minimal changes to the architecture of clients, to the contents of blocks, to the interface with nodes, and yeah, that's really the main thing we wanted to get, is just having this be a really smooth transition for users of Ethereum. And now that the merge has actually happened, there's a few nice charts I wanted to highlight that I've seen since then. The first one is this. This is from CoinMetrics, and I actually couldn't believe this chart when I first saw it. It shows what the average block time is pre and post merge. So this is taken in like the 12-hour gap where the merge happened. Merge was at about 6:30 UTC, which you can see clearly on the graph. And before the merge, like I was saying, we had this target of 13-second block times, but we had very high variance in it. And I think I personally underestimated the amount of variance that we had. So if you look at this left part of the graph, all of the red dots are short blocks that happen in less than 12 seconds, but this entire upper part of blocks that take more than 12 seconds is quite surprising. And even if you look after the merge, you can see there's this red line which shows that like most blocks come every 12 seconds, and there's a couple kind of blue dots which show that this validator was offline. So the next block didn't come in 12 seconds, but it came in 24. And so far, there hasn't been like 2 validators offline in a row. So you haven't seen like a 36-second block on proof of stake Ethereum. And I think it just shows like how much more predictable block times have become under proof of stake. So you kind of know that you can expect something basically every 12 seconds. And if not, might be every 24 seconds. Whereas before, it's kind of wild to see we had blocks that would take between 60 and 80 seconds from time to time. And that those happen, multiple times between this in a 6-hour span. And then related, there's a couple other neat things to notice well, the first one on the left here is a chart from Etherscan looking at the daily gas usage. And it shows that if we went from 13-second to 12-second blocks, obviously there's going to be an increase in capacity on the network. And we can see that quite clearly in this chart. So you can see towards the end, the last couple of days or when the merge happened, and you see the gas use daily has gone up. And one thing that's nice is we've managed to increase the capacity a little bit, and we've also managed to get better pricing on the network. So if you look at this, the right-hand side, the quoted tweet from Martin is basically the same thing as this chart that I showed before, just in a different view. But Vitalik's reply there is saying that the amount of full blocks we've seen has gone from 20% to 10%. And this is quite important because the mechanism we use to price gas on the network, EIP 1559, you can think of as basically surge pricing for Ethereum that goes both ways. So when many people want to use Ethereum, the price goes up. When no one wants to use Ethereum, the price goes down. And the way we're able to calibrate this is by trying to keep blocks 50% full all of the time. So if blocks are 50% full, we assume that the demand is constant, so we don't change the price. And if they're more than that, we start raising the price. And if they're less than that, we start lowering it. But this means that if many blocks are more than 100% full, right? Like there's more than twice as much demand as the current base fee, then our mechanism kind of stops working, right? It stops tracking the excess demand because it gets saturated. And it can take many blocks to kind of recover from that. And one of the reasons this can happen is not necessarily that there's more demand, but it's simply that there's more time between transactions, right? You can think that if blocks are supposed to come every 13 seconds and one of them comes every 26 seconds, which as you can see on this chart is quite common, it'll look to the network as though there's twice as much demand, but in practice, per unit of time, the demand was constant. And so because we have these much more constant block times now, we see that we actually have less blocks that are 100% full. So we went from about 20% to 10%. And that's great because it kind of shows that our current pricing mechanism actually works better in a post-merge world, and it gets kind of distorted less often by surges in demand. So I wanted to share these couple charts because even though it hasn't been super long since the merge happened, we're already seeing some interesting effects on the network, and it's clearly shown that things are generally more stable. So that's all I had. Thank you so much for having me, and I wish you a great conference. Cheers.